Hello, welcome back to another lecture. In this lecture, I wanted to design a round timber column. Now, when we look at the NDS section 3.7 I have on the board, it kind of says round column, you can design it the same as a square column as long as you have the same cross-sectional area. They've done a great job. They really, my hats off to them. But they could have gone a little bit more, put another page or two in there, in this section, put in a buckling equation for round column, and also to put another table and table for 1B for the cross-sectional property. So what we're going to do here in this lecture, I'm going to go ahead and design a round column. At the same time, I'm going to design a square column, and with the identical cross-sectional area, and we're going to go ahead and compare them all the way down. We're going to select Southern Pine number 1 dense, and if we go to table 4D of the supplement, we can find out the FC comes out to 975. Let me write all the property down here as I'm here. From the same table, we can go ahead and our E minimum module from elasticity in the X direction is 580,000 psi, and this is going to be for a round column. So we're going to have a column here. And let's say our column is basically a pin on both ends. Okay, and give it a length of 15 feet. And a cross-sectional area, this one is a square. So I'm going to go ahead and do the same column over here. And I'm going to make it a round, same exact column with a different cross-sectional. So let's come up with the cross-sectional area for this. What I have here, if we select 10 by 10, which that become 9.5 actual size by 9.5, so my area, it's going to be, this is from table 1B, it's going to be 9025 square inch, and let me write that down. This is NDS supplement 1B. That's where you find that. So if I go ahead and, before I continue, I'm going to do the round column. If I go ahead and design a round column with the same identical, it would be diameter 11 inches. Or say actual size be 10.75, and my area is going to come out to pi r square or pi 4 divided by d square, and if I calculate that, that's going to come out to 9071. So they're pretty much the same, and same FC, same species, same exact wood. So FC for the round column is going to be same thing, 975 from that table, and my E minimum is going to be 580,000 psi. PSI. Okay, from table 4.31, from NDS 4.31, we have our F prime C is equal F star C time CP, that's for the buckling, and equal FC time CDCM CTCF CICP. And that's equal, F prime C comes out to 975 time, here before we continue, it's going to be one thing we didn't mention for CD. We're going to have a snow load combination here. So that means our CD gonna come out to 1.15. And it's going to be dry condition. CM is equal 1, CT is equal 1. Size factor from table 4A comes out to 1, and CI is not going to size in factor, so CP. And therefore, we're going to have 975 times 1.15 times 11 and CP, so that comes out to 1121 CP. Basically, 1121 become F prime, FSC star. And our E prime minimum comes out to E minimum time going to be CM, CT. The other factors are really 1, so become 580,000 time 1, which is 580,000 PSI. And if we continue with these right here to the circular one, these same thing applies here because it's the same species, same length, same exact thing. The only thing is different is the cross-sectional area. So my F prime C over here for the circular column is going to become same as here, 1121 CP, and my E prime minimum is going to be 580,000 PSI. All right, now we have got that out of the way. All right, so the next thing we're going to go ahead and continue is going to be column stability factor, CP. In order to calculate that, there's many things we need to know. And I know, and you should watch my column design on timber or on a steel that I have. Explain why column, the buckling is so important. If we have a column, and if you load the column correctly down the center and everything is plumb, P is over A. But that's not the case. Normally when we have an issue with the buckling. And that's why really a lot of column fails way before they reach their strength. So one thing is here that we're going to have to calculate the buckling and cylinder ratio to calculate the stability factor for the buckling. And let's if you look at the section 3.1.12, and that's where we're going to calculate all that stuff. Also, before we get this, we mentioned that this column was a pin on both ends. And if we look at the appendix G, and that gives us the K factor, it's going to become equal 1. So our K factor from appendix G, K is equal 1. And now we have that, and we go to say the effective length. Our effective length is 15 feet because really it's an unsupported length that is not supported sideways. So it's going to be a 15 feet, and therefore from that same table we're going to have LE is equal KE times L, K times L, and that's going to become 1 times 15 times 12, and that's come out to 180 inch. And this will stand the same thing, and our LE is going to be same thing here, which is going to become KL, which is 180 inch. Same thing. So again, looking at the same section 3.7.13, we are concerned about LE divided by D. In our case, it's going to be 180 divided by D, and our D is 9.5 inches, and that comes out to 1894, which is less than 50, and we're good here. Okay, when we I'm gonna let me finish this. I go over there because I want to explain that a little bit more. And so now we have this. We're gonna go find out FSCE, and FSCE is critical buckling design value. Let me write that down. Okay, so if he is a critical design buckling value, and that the equation is given in section 3.712, and FSCE comes out to 0.822 E prime minimum divided by LE divided by D, the whole thing squared. So in our case, it's going to come out to 0.822 times 580,000 and divide the whole thing by 1894 squared. And my FC critical at the buckling design value comes out to 1329 PSI. So now you have that. This will help me to calculate CP. I'll come back up here, I have to erase this stuff, but I'm going to move over on the other side. And one of the things is that in NDS, they don't provide critical buckling design value for circular column, but there's a formula out there. You can find it from an older book or a timber manual, design manual might have it in there. And so we're going to follow the same procedure. We had LE here, and our LE came out to 180, which was 180 here. Next, we want to find LE over D. In this case, because it's circular, it's going to be LE divided by the diameter, which is 180 divided by 10.75, and that comes out to 1675, and we still less than 50. We okay. Circular column design, they are really good. They have a lot of good property. And one thing in here I want to the critical buckling design value, which you cannot find in the book, is FCE for circular column is 0.617 times E prime minimum, and divide that by LE divided by diameter square. In our case, it's 0.617 times 580,000 and divided by 1675 square. So my FCE come out to 1275.5. Okay, so now we have got that. I'm gonna go ahead and erase this. This is amazing. I came up with this new technique. It's a new electronic, and all you gotta do is snap your finger, say 1, 2, 3, and everything cleans up. Watch this. 1, 2, 3. Huh? I told you. Yeah, you smile. I can see you smile. You got a little bit of a smile on your face. And if you got a little bit of a smile on your face, go ahead, push subscribe and then give me a thumbs up. Anyway, let's continue. So now we have all this, and the next thing we're going to continue with is we knew our FSC came out to, in this one when we calculated, I just erased it, of course. FSCE came out to 1329, and here FSCE came out to 1275.5. Okay, so what I want to find CP. Before I find CP, I want to say FSCE divided by F star C, and which that came out to love. This one came out 1329, and this one came out to 1121, and that gave me 1.186. Why do I need that? Because of this formula, which I got on board right here, CP I'm going to write it down in a different color, smaller, because this formula Cp is equal 1 plus FSCE divided by F star C, and divide the whole thing by 2C. And 2C, our C is equal 0.8. If you look at that bottom of the section 3.175, it says C is equal 0.8 for sawn lumber. And that's where we are. And then it's going to be minus square root of, same thing here, basically square it, 1 plus FCE divided by F star C divided by 2C square minus FCE divided by F star C, and the whole thing divided by C. Okay? Now you can use your calculator. I have all these values. I put all these values into there, and it's going to become 1 plus 1.186 divided by 2 times 0.8 minus square root of that came out to 1.366 square, and that one came out to minus 1.186 divided by 0.8. So my CP comes out to 0.745. And if I go ahead and continue on this side, my CP comes out to same equation. It's going to be, of course, my FSCE divided by F star C comes out to 1275.5 divided by 1121, which that gave me a 1.137. My CP comes out, okay, so my CP comes out to 1 plus 1.137 divided by 2 times 0.8 and minus square root of, this comes out to 1.335, I think. Do my calculation, I could be off a little bit, minus 1.137 divided by 0.8. And CP comes out for this one 0.735 and 0.745. It's almost identical. Of course, the cross section is a little bit different. And the next thing I'm going to continue, I'm going to come back in here. We found out our CP. Now we're going to find out what F prime C is. All this was to find out what F prime C is. So F prime C is equal 1121 times CP, which was 0.745, and that gave me a value of 835.1. Okay, and of course how much force I can put on this column before I can break it at this condition, which is not braced for 15 feet, it's going to be P. It's going to come out to my design value is going to be that F prime C times the area, which is BD in this case, and that comes out to 835.1 time, and BD came out to 90.25, and my amount of load I can put on here is 75 kips. 75,367, or I say 75 kips or pound. Come back to this way, and we have the same thing here. So we're going to go ahead and say F prime C comes out to 1121 times 735 and that will give me 823.94. Very similar. And then my amount of load I can put on here, P, it's going to come out to 823 times the cross-sectional area, which was 9071, and that gave me about 74,739 pounds. Really, the difference is not much. If I divide that number by this number, 74,739 divided by 75,367, that comes out closer to 99%. Very close. However, if you follow the NDS, sometimes you might be 4% over, which is kind of overestimated, but you can go ahead and design your own round column. Using this procedure, using the formula which I got rid of, the formula was for critical buckling design value, and that's it. And you don't have to go through all this and converting back and forth. Just use this. And I hope the NDS in the next time when they update their book, they put this in there, this 2 section in there, and make it a lot easier for the designer. One thing I will caution you is, do not confuse this with round timber pole or pile. We're not doing timber pole or pile, we're doing column. It's a big difference. Well, thank you and have a good day.